Okay, so starting the last section of the course here, which is 20.2, we'll be talking about Euler's equations, which, we introduced last time 3D kinematics, so kinematics of rigid bodies and full 3D motion, and went over some examples. Now we're moving on to what we want to get is the three-dimensional equations of motion for rigid bodies, and so that's what just relates the forces to the motion that those forces cause. So this lecture and the next one, so this lecture is actually going to be mainly focused on a geometrical property like the moment of inertia, but generalizing it for the 3D. And so all that is this moment of inertia is now extended into 6 components of a geometrical property related to the moment of inertia, where the moment of inertia is just like really like half of those 6 components. And then that will be needed in our equation of motion. Okay, so and that those moments of inertia extended as 6 components is actually in the appendix to chapter 20, and then some of those values are found in appendix C in the book. So this lecture focused on those geometrical properties. Next lecture will be actually on Euler's equations, which is the last theory of the class, and then we'll wrap it up with a lecture with some examples of these 3-dimensional dynamics problems, essentially. Okay. So in terms of the 3-dimensional equations of motion, the translation components is just Newton's second law, and is the trivial extension of our study of particles, so particle dynamics. Except the only thing we need to be careful with is that this acceleration here is for the center of mass. Okay. Now we then add to it rotation for general 3D motion, and there's a lot of work to be said here. In fact, we've got some derivations to get through, so we'll just say, oh boy, here we go. Okay, lots to fill in, lots of details. Main focus here today, or in this lecture, main focus here is on the setup, where we actually won't even be deriving it. The full equation of motion that belongs here for the rotation is next time. Okay, I think we got our framework now. So in order to talk about rotation, we need to talk about angular momentum, which we've already done. So we'll be reviewing things a bit here, and then getting it to look like this. And again, when we introduced angular momentum, we had a version that was in fully general for 3-dimension, and it looked something like this. So angular momentum about some point A is the angular momentum about the center of mass, plus a term that is for the relative motion, for the relative angular momentum, essentially. Okay. And that looks like this. And why we're doing this is that this is now relates the angular momentum about a point. Maybe this is the point about which the system is rotating to the angular momentum about the center of mass. And why are we doing that? Right, so we can relate it up to Newton's second law, which is written intrinsically for the center of mass. So. Let's define all these terms. This is the body's angular momentum about A, so about some point A. This here is the body's angular momentum about the mass center, about the center of mass. And so let's put some arrows there. This here, let's go with this one, right? This is the linear momentum of the body, and finally, so what happens when we're crossing a position vector, a relative position vector, right? So we're getting it is the moment of this linear momentum, right? So relative position A to G. Okay, So we got angular momentum at A is the angular momentum about G, and then the moment of the linear momentum of the system, or of the body. So to combined here, this is the moment of linear momentum of the body. Okay. So then we have an expression for hg, okay, where the angular momentum about the center of mass is defined this way, right? Integral over the entire mass of these, and we'll draw a picture to go with this, right? That relative position vector to a dm element, so a differential mass element. This is our angular moment or angular velocity of the body crossed into that relative position vector once again, integrated over tiny mass or all of our mass elements, right? So the picture that goes with this is right, some, I don't know, I put arrows on it, I don't usually do that. There is the origin of a coordinate system. We've called this before, if this is primary, right, we call these like capital X, capital Y, just some way to differentiate it from the coordinate that we actually write our, description of motion and our equations of motion in. So then we have a body up here, okay, and that body then has a center of mass, and that center of mass could have, well, a non-zero velocity. So generally there is some velocity of g, where this is point G. Okay, and then we go to some tiny mass element, some differential element of this macro scale mass. So the whole thing has mass m, but we have a little element of it here, dm. Okay, and this is that relative position vector. Okay, that is, can I fit it in here? The relative position vector 2dm from G. Okay, well now the whole object may be, let's say the whole body is then rotating. So not only is the center of mass translating in that direction, but maybe there's a point here about which, and now remember this is a 3D object, so there's a point here where, right, there's some axis of rotation at this time shot, right? So we'll put an omega there, and this is actually a vector omega about which the system is rotating, right? So the actual body, or I say system, and it's like the body. The body would then be rotating like this way. Okay, so it'd be something like that, yeah? That's kind of hard to visualize, but the body would be kind of rotating that way, about that point. If that's the case, then what we're actually doing here, what we want to do is affix our secondary coordinate system here. Okay, and so maybe it would be convenient to, at this point, put a, I don't know, there's maybe the y now, maybe the x and z come out that way, x, y, z. And so oftentimes we'll be having this rotating reference frame up for that, that is the rotation of the body here, and then inside the body we just have these relative position vectors inside the rotation, right? Okay. So recall one thing about, now back to our definition. Let's put this like in a little bubble here. Let's just remind us of the pictures we're looking at here. Okay, so recall something we had before. So when we assumed 2D planar motion, right? This is now general for 3D motion. What we did back then was we assumed that our rotation of the body, which is that blue vector over here, we assumed that the rotation of the body, we could just align it with the k-hat direction. And so if we were to do that, we'd actually, maybe it'd be better to we would like line up this coordinate system here with the z-axis right in line with omega. And that would mean that the whole body was only rotating, right, about that axis, right? And then we would have our dmg, that would be some sort of, x I hat plus y j hat. right? As that would then be in the this motion, this relative position vector would only be could only be in the I hat j hat plane, or the xy plane, where k hat would be out of the plane, right? In fact, we could make it planar motion by syncing that up, right? Syncing that coordinate system up in this fashion. Okay, so remember we choose the coordinate system to be this way. This is really what we're saying for convenience, right? So if we can describe, if this is allowed based on the motion, then we should choose our coordinate system this way, because it's going to be a good choice. And it just means that it limits our motion to be in the plane if the rotation is out of the plane exactly. Okay, so in that case, why it was so convenient is then we could define hg to be well, if you look back up at the definition, right, if these are in the plane, that's out of the plane, and do the cross product and you're really careful, it really turns out to just be the magnitude of this relative position vector that's in the plane times omega in the k hat direction, and we would integrate. This is the only thing that changes with the little differential mass element. Okay, that's supposed to be like a bracket of some kind, right? That's our integral right there. Well, not only is that an integral, but this is the moment of inertia about g, about the center of mass. Okay, so that's how we got to this a previous relationship, which was that the angular momentum about the center of mass is just the moment of inertia about the center of mass times that rotation vector, right? Because this is really another way to write this term here. That is the omega vector, or the angular velocity vector. Okay, now when we go into 3D, okay, so when we have 3D motion, we can no longer make these assumptions, right? In general, our rotation now has components in all directions, an omega x I hat plus an omega y j hat plus an omega z k hat. It really comes down to that there isn't a choice for a coordinate system that makes this convenient, right? So if we do choose like the omega, the rotation of the body to be just omega k hat, then the relative position vectors aren't going to work itself out that they always stay in the plane. Okay, so also our general position vector to get to our little dm elements from our center of mass has components in all three coordinate directions. Okay, x I hat j y j hat plus z k hat, kind of as we've drawn it here, right? To go anywhere here might, it's truly three-dimensional in nature. Okay, so I don't have enough space here, but what we're going to do is, this is for 2D planar motion. This is a general description, right? But when we plug into these quantities into here, we get the following equation. And I'm going to write all of this out. But it's going to be a matrix equation first, and then I'll actually write it all the way out. So let me write it out, and we'll come back and talk about it. Okay, so there it is. So the way we wrote this, now remember how we got here. For 2D planar motion, when we could make these substitutions, we would get hg. Well, let's actually write it out now, right? So what this said, for 2D planar motion, hg was some moment of inertia about that center of mass times the omega vector. Okay, in full 3, and that's just a result of making these observations, or making these definitions that we can do from the 2D planar motion assumption, and plugging that into the general form, which is right here. Okay, now if it's not general, instead we have to plug all three components into every single three of these three of these components of the double cross product, we get a general form that looks like this. And what this is that the I hat, j hat, k hat component of the angular momentum each has three terms that each could depend on the individual components of the angular velocity multiplied by something that looks like a moment of inertia or an I. Okay, so let's label these. Yeah, what we're seeing here. Now, this is a matrix equation, so just remind us what that is, right? So that means take a row here, multiply it component by component by this one column, and that gives you the first element. Okay, so you see Ixx omega x, and then the next plus a negative Ixy omega y plus a negative Ixz times omega z, right? To get the next term down, you take this row and multiply it component by component by the column there, and then add them up, and that's the j hat component. And the way we can get to the I hat, j hat, k hat is actually multiply it before by a row of the I hat, j hat, k hat components. So you take that times that, that times that, that times that. That gives you three entries, and then you multiply those three entries by this I hat, j hat, k hat, and then you get this ending result. Okay, so in the end, this is it all written out, and this it is in matrix form. But this is the angular momentum vector, right? Okay, so it might be ugly looking, and we haven't even gotten to the equation of motion, right? This is just describing what the angular momentum is. Okay, these diagonal terms are unique in that they're not negative, and they have the same subscript, like the double subscripts. These are our moments of inertia. Moments of inertia. No different than we've defined them before, and I call them MOI. Okay, anything else, the off diagonals here, so that's these guys and those guys. These are called our products of inertia, and we will see why they get those names by the end of the lecture here. But so POI, POI. Okay, now this we can then rewrite, we can really simplify this equation in just an expression that just tells us what we're looking at here. We're saying the angular momentum about the center of mass is then a matrix I, and the book uses this notation to represent a matrix. If it's a 2D matrix, I usually do like a 2 bars over the top, so I'll just do a mixed combination, right? Because the book can do bolds, and I can't really draw bold here. So we'll just represent a double bar, so for a 2-dimensional matrix of the I values. Okay, so that's what this whole thing is. Okay, products of inertia. My label there kind of got in the way. This is what we call the inertia matrix. Hopefully you see why we're calling that products of inertia, moments of inertia, of the rigid body, right? It's really a geometrical property that describes the rigid body. Remember, your moments of inertia are those resistance to motion, but it just comes from summing up mass distribution. Okay, and then again, we give it the symbol I with brackets, maybe 2 bars over the top. Okay, you might also hear this called a tensor. Okay, so also known as a tensor. The matrix, or the inertia tensor. Tensor is a kind of a fancy word for a matrix that has special properties. Okay, so we are not going to go any further with our equation of motion with Euler's equation. Again, back to the start of the lecture. That is the focus of these collection of this section, is to get to the equation of motion. We need to talk about these geometrical properties and what they are here, because we haven't even gotten to the equation of motion. We're just talking about angular momentum in 3 dimensions, and it already shows these complex properties. So that brings us to the main focus of the lecture today, which is the appendix in chapter 20. Okay, which are basically describing the moments of inertia and products of inertia in 3 dimensions. Okay, so the moments of inertia are defined, well, remember what these are. These are no different here in 3 dimensions than planar. This is a measure of resistance to rotation of a body. Okay, it's really a property of the shape, property of the body, and we got three of them, right? So we have Ixx, which is defined to be, all right, take your y squared, so if it's x, and take y squared and z squared, add them together. Those are the coordinates of different points on the body, because we're integrating over mass elements of that body, right? And then Iyy is going to be the sum of the x squared plus z squared coordinates, and Izz is the integral of x squared and y squared coordinates over the entire mass. Okay, and these were the moments of inertia. Those were the diagonals of that inertia matrix that we saw saw up here, right? Okay, and now that's a new definition for something that we've seen before, the moment of inertia. We used to just use the r value, it was r squared dm, right? Well, now it's the r value, that's just the kind of distance from the origin, but this is like truly a distance from like one of the axes. So this is the distance from the x-axis. This is the distance from the y-axis, distance from the z-axis, right? Well, in a way, right? Yeah. Okay, so let's see here. What can we say? Oh yeah, products of inertia. Okay, so we're going to make statements about this. Here we said, just reminding ourselves what the moment of inertia really means. When we get to the product of inertia, first of all, Ixy, you see that there's like 6 of them here, right? 6 off-diagonal entries. There's actually only 3 unique quantities there, and that's because it doesn't matter which order the subscripts are in. They have the same definition, which is because they're a product. The integrand is a product. So xy dm. So here we're integrating the product of the xy coordinates over the entire mass of the body, right? So those two different entries are actually hold the same value here, so they're not unique. Okay, and that the same definition follows. So Izx equals Ixz, which is the integral of x times z over the entire mass, and then Iyz equals Izy, which is the product of yz over the entire mass. All right, and these are our products of inertia. Those are the off-diagonal elements. Now these we have to, maybe we have to be more careful with these because this is kind of a new property. What this is a kind of a coupling, or measuring the coupling of the motion that we have along one direction to the angular momentum in the other direction. Okay, that's what this is what this is used for. Okay, this is really a measure of imbalance or asymmetry in the body. Okay, and now these, whereas the moments of inertia are only positive geometrical properties, these can be positive or negative, right? Because x can be negative. So if it's negative, it means that the body is skewed towards the negative, one of those negative axes, or across one of the negative half of those axes. So it can be positive or negative. Right. Okay. Now these properties, again, remember Appendix C, which had all of those typical shapes? Those have products of inertia in them as well, and those shapes were three-dimensional in their nature. Okay, so we'll just add here that we can refer to Appendix C for moment of inertia and product of inertias for common shapes. And so our discussion here is the appendix of chapter 20, but we also use the appendix in the back of the book, Appendix C, to actually get at some of those quantities, to actually get the moment of inertia for particular shapes. Okay, I need to dig it out of my notes here, but I'll actually pull up that table here. Okay. So here's at least the first page of it, right? Here's that slender rod that we've looked at so much, right? 1/3 ml squared is about the end of the rod. 1/12 ml squared is the moments of inertia about the center of mass, Okay, but the products of inertia here are these cross ones, and you see those are all 0 here for this shape. We get a shape where they're not all the way 0. Yeah, maybe like the hemisphere. Okay. You see moments of inertia, XX, YY, and I was just X, but that's about the X-axis, so that's IXX, and then you have IX prime, IY prime. Oh, they don't give the product of inertia there. Yeah, all of these shapes have 0 product of inertia, which is what we're looking for actually. Here's one, right? So a thin plate, right? That one has a non-zero product of inertia, although it depends on what the product of inertia is there for A. Okay. Yeah, I don't see any other ones. Here's one, right? Rectangular plate, right? Non-zero because it's off of the axis, right? So there's no you see how most of these have 0 products of inertia because there's a lot of symmetry going on. Right, so here's a symmetry. Our coordinate is right through the center. All of our products are 0. All of the products of inertia down here are 0 because of the symmetry with the rectangular prism being right, the origin of the coordinate system being right in the center of the prism. Right, but in this case, if we put the coordinate over here at a corner, there's really no symmetry across an axis, so we have a non-zero product of inertia. What we're going to look to do going forward with our problems is find a coordinate system, find a reference frame where we can cancel out all the products of inertia, and that's going to make our analysis much better. So let's talk about the typical shapes that hold that property to be true. Okay. Before we do that, we need to talk about composite bodies for these moments of inertia and products of inertia. And we've already done this for 2D planar motion, and there's nothing new here. We just need to extend it to our 3-dimensional analysis. Okay, composite bodies and the parallel axis theorem. Okay, so let's put in a coordinate system, nice big one here. Okay, this is X, Y, and Z. And let's put our body out here somewhere. Okay, just some 3-dimensional shape. I'm limited to drawing in 2. Let's say the center of mass is there. And, right, so if that's X, Y, Z, let's put the origin as A, point A. And we'll put a different coordinate system up here, right? So we'll call this Z prime, Y prime, X prime, okay? Remember, we also had before that this worked for all 3 dimensions. Where is the center of mass? Well, we can follow it down. We can take wherever it's down and march that backward. We can march that over to here. And this distance here, right, that is y bar. That's its y location. Oh, yeah, that distance is y bar. That distance is x bar, and this height is z bar. Right, that's what we calculated with our center of mass. That gets us from the principal axis here, A, the primary reference frame A at its origin, and within those coordinates, where do we have to go to get to the center of mass of the object? Well, that's a y bar down the y-axis, an x bar down the x-axis, and a z bar up the z-axis. Okay, so if we want to then take the moment of inertia about point A, okay, and we know the moment of inertia about the values here, or we just want to relate them. We want to relate the moments of inertia about x, y, z to x prime, y prime, z prime. We just apply the parallel axis, but it's a little bit different here. Prime prime plus, there's m, and we said d squared before, but this is now not the total distance squared, but we take the z value squared and the y value squared. Okay, so it's just part of that total distance. I is y prime plus m x bar squared plus z bar squared, and then z is z prime plus the mass, and then this is going to be x bar squared plus y bar squared. Okay. When it comes to the products of inertia, we got a parallel axis there as well. So getting a product of inertia about A when we have it about the center of mass looks like this. Ixy is Ix prime y prime plus the mass, now the product x bar y bar. Ixz is Ix prime z prime plus the mass x bar z bar. And Iyz is Iy prime z prime plus m y bar z bar. Okay. All right. So again, right, these are just geometrical properties. We know they're a part of the definition of angular momentum, and so therefore they're going to play a role when we get to the equation of motion, right? The Newton's second law version for the angular motion of 3D bodies, and that's why we need to just talk about the geometrical property. Now, the goal is we're going to look for something where we do this transition to some sort of coordinate axes where all of these products of inertia drop to 0. That's going to help a lot of in our analysis. And if not, all right, if that's not possible, well, then we need to know how to calculate them. Let's see if symmetry can do this, right? Okay. Let's look what symmetry does to different types of symmetry we have in shapes. Okay, so one is called plane symmetry. And what that means is that an object is mirrored on either side of a plane. So for example, if can we draw something? So let's have an example where if the x prime y prime plane is the mirror. I'll put that in quotes because it's not actually a mirror, it's just that's where the shape is mirrored. And so what we're saying is this is where z prime equals 0. Okay, can we draw this? Okay, let's see here. Let's draw a shape, and we'll just make it like a big pyramid, kind of. Okay, where then this kind of goes up. And then it kind of goes back and up. I don't know, it seems impossible to draw. Okay, so the intention there was, and then that goes up there, and then there's a line that way. That's pretty good, I think. That's pretty good. So now we go to the center of mass here, and like that's right in the center there, and we put the y-axis coming, the y-axis coming straight up, the z-axis, the x-axis would kind of come that way. And then the z would be straight out through this bar. And again, there might be some other symmetries here. I was trying to not make that. I was just trying to make this. This is almost impossible to do. Okay, I was just trying to make this mirrored about, so like the plane xy, there, that plane you see there, right? If then you take that plane that defines, or z prime is coming straight out of it, and if that acts like a mirror, then we know for sure that Iy prime z prime and Ix prime z prime equals 0. So all of these products of inertia that have the z prime in it, right, are or I guess it's if the plane is in the xy plane, the mirror is of the xy plane, then it's these cross, the product of inertia with those coordinates together with the one that's not. Those ones are 0. That's just how it turns out to be. Okay. Trying to look at this. There's not a symmetry about xz here, right? There's no symmetry about xz, right? And because what I tried to do is have like a flat bottom to get with like a point, like it's kind of like a tent. Right, so xz definitely doesn't have symmetry, but I think you could make the justification that y prime z prime is also a plane of symmetry, and so in that sense, if that's the case, then we would also have the other product of inertia is also 0 here. Okay, but that's just right. If I was able to draw a shape that was only plane symmetric with one plane, then this would be true. Okay. Next kind of symmetry, and again, we're looking to like make our problem simpler, where we can cancel out or just use as 0. We can just go into the problem without doing calculations for these products of inertia. So we also get it with rotational symmetry, and what we mean is there's no change if rotated, no change in the shape if rotated about an axis. Okay, so this one I can actually draw, I think. So example is take x, y, and z, and then about that z-axis we have a cone. Okay, so the cone is kind of coming there, and making like a circular shape. Oh, I already messed it up. Okay. Maybe it's not as easy. I was so confident. All right, there should be a cone where the z-axis comes straight out of it, right? Straight out of it. Yeah? Okay. If that's the case, then no matter how you rotate it about the z-axis, there's no change to the shape. You take a snapshot, looks the exact same, looks the exact same. Now if we rotate the shape about the y-axis, right, that would take the cone and then start moving it this way. Well, now there's definitely a change. I mean, the shape doesn't change, but it's like where the particles are, where the mass of the object is, changes. Rotated about the x-axis, that would take the cone and sort of rotate it this way. That's definitely changing it. But it is rotationally symmetric about the z-axis. In this case, and this could be about any of the rotational axes, all of the products of inertia are 0. So all POIs are 0. What we mean is IXY equals IXZ, which equals IYZ, which is 0. Also, if this is symmetric about the z-axis, then the other two moments of inertia are the same. I mean, we don't know what they equal, but they're the same. And you can see that, you can look back in Appendix C. There is a cone, and the two that are not the axis of rotation are the exact same. All right, this would be huge, right? If we can then determine rotational symmetry, it's a huge jump into simplifying our problem. Okay, we want to end this with basically look for, in doing these problems that are coming up here. Again, we still have to talk about the theory to get to the equation of motion, but know when the examples come, when the homework comes. What we're looking for is a principal frame. We're looking to set our coordinate system in a way such that we have rotational symmetry, right? So no matter how we get there, this is some orientation, some coordinate system where all the products of inertia are 0. Okay, so what I mean by that is no matter what it is, this inertia matrix is just some inertia, some other inertia, some other inertia, right? Those are the moments of inertia, but all of these are 0. Okay, and so this might take a shift in your coordinate system, so it's not x, y, and z. It's some, where the coordinates are whatever, some E1, E2, E3, whatever you want to call them. There's a shift in the coordinate, or a translation, a rotation of the coordinate system, such that this is true. That's a good, that would be something that's going to make our life easier, right? So we're looking for setting our products of inertia to 0. We can do that by looking for rotational symmetry natural in the shapes that we're looking at, and then aligning our coordinate system such that one of the coordinates is straight down the axis of rotation, right? Or the axis of symmetry, of rotational symmetry. Okay? Okay, so that's where we'll leave it. We're going to come back next time, and now that we've talked about the moment of inertia, we can then apply it in our derivation of the equation of motion. We'll do that next time. After that, we'll follow it up with one lecture of sample problems for these true 3D, three-dimensional dynamics problems, and that is it for the class.